Hello everyone, welcome on our YouTube channel Physics Made Easy Quota, where you can study physics in online series. So this video is regarding the alternating currents and we are going to understand few concepts of the alternating circuits. So now we check the phasor diagrams. So first of all, the diagram for the pure resistor. So in this diagram you can see that the phase difference between the current and the voltage is zero, because it is observed that both voltage and current have same zero, maximum and minimum values at the same time. So from their comparison we come to the conclusion that the voltage and the current across the resistor are in phase. Now the next topic we are going to understand about the alternating voltage applied to an inductor. So such a circuit is called as a purely inductive circuit. So for such circuit we know the voltage applied across it, V is equal to V naught sine omega t. The EMF is induced across the inductor, which opposes the growth of the current in the circuit, and EMF is given by minus L di over dt. Since there is no potential drop across the circuit, so the total potential is V minus L di over dt, and by rearranging we have the value di over dt is equal to V upon L. Then we know the value of the V, so just change it with its value V naught sine omega t. After doing the mathematic calculations, we have the answer I is equal to V naught L omega multiplied by minus cos omega t. Then apply the trigonometry function. We can change the cos omega t into sine omega t minus pi by 2, and the things, that is the V naught divided by L omega is equal to the I naught, which is called as a peak value. Hence our equation is modified into I is equal to I naught sine omega t minus pi by 2. So what about the phasor diagram for pure inductive circuit? We get two equations, one that is the voltage across the inductor, and the second equation that we solved in the previous slide is about the current across the inductor. By comparing both these equations, we see that current lags behind the voltage with the difference of the minus pi by 2. So it means that current lag behind the voltage by an angle of pi by 2. This can be represented in the given diagram. So you can see the phase diagram as the voltage is leading the current. So voltage is leading by the angle of the 90-degree that is shown in the phasor diagram. Voltage is in the xy positive plane and the current is in the xy dash plane. Similarly, we can draw the time diagram for along with the phasor diagram. So from the time diagram we can see that there is a phase difference, as there is the variation in the initial point of the current and the voltage, as when voltage start from the origin O, and therefore at the same time the current is lagging behind and it start from the minus I naught. Now we can calculate the inductive reactance. Inductive reactance is actually the resistance. This is a resistance or the opposition offered by the inductor to the flow of the current in the circuit. In other words, we can say that inductive reactance play the same role in the AC circuit as the resistance play in the DC circuit. So we know the formula of the I naught is equal to V naught divided by L omega. So apply the Ohm's law. According to the Ohm's law, we have I naught is equal to V naught divided by R. Then we compare both these equations, and as we can see clearly that the L omega has the same dimensions of the resistance R. So L omega is known as the inductive reactance. So L omega is known with the new symbol xi L, where omega is equal to 2 pi nu. So the xi L is equal to 2 pi nu multiplied by L. Now this graph shows the variation of the XIL with the frequency. As XIL is given by the formula 2 pi nu into L, which means that XIL directly proportional to the frequency for an inductor. So this graph represents that XIL increases linearly with increase in the frequency of the current. Now moving ahead with the alternating voltage applied to a capacitor. So in this circuit we only had a capacitor, and this circuit is known as a purely capacitive circuit because the alternating source is connected to the capacitor, which is named by the C as shown in the diagram. So first of all, as the voltage is applied, so we aware about the formula of the alternating voltage. V is equal to V naught sine omega t, and let Q be the charge on the capacitor at any instant, and we know the formula of the potential difference, that is equal to Q upon C. But in this case we can replace the Vc with V, that is the alternating applied voltage. Then interchange the things, we get the value of the Q V naught C sine omega t. Then we know that the value of the current for the small amount of the charge flowing through it is dq divided by dt. Just replace the value of the Q with the formula V naught C sine omega t. Do the derivative and we come to the equation V naught cos omega t divide by 1 upon C omega. So now we can interchange the cos omega t in the form of the sine so that it is easier for us to compare the equation of the current with the voltage, so that we can draw the phase diagram. So we could change the cos omega t in the form of the sine, that is the sine omega t plus pi by 2. So the final answer for the current is I is equal to I naught sine omega t plus pi by 2. So now we are wondering what is I naught here. I naught is actually given name to the values, that is a V naught divided by 1 upon C omega, which is called as a peak value of current. So we can compare the equations now for the current and we can compare it with the equation of the voltage. So now after comparison we see that the current leads the EMF by the angle pi by 2 for the case of the pure capacitive AC circuit. So in the phasor diagram you can see that current leads the voltage. Current leads the voltage by the angle of the 90 degree, and if you compare the phasor diagram with the time diagram you can clearly observe that the current is leading the voltage. Capacitive reactance is the effective opposition or a resistance offered by a capacitor to the flow of the current in the circuit. We get it equation by comparing the value of the I naught with the Ohm's law, and we conclude that 1 upon C omega has the same dimensions of the resistance, and this is denoted with the symbol xi c, which is known as a capacitive reactance.